Coming to a key facet of artificial intelligence, we explored that optimization is a key element of artificial intelligence. We also, have several flavors of optimization. It could be in form of heuristics. It could be in form of, taking off from classical work, which is intelligent programming, linear programming, and moving on to a very specific form of constraint optimization, which is basically rooted in AI. So if you see, the whole notion of optimization is having its manifestation in several areas of AI. For example, in ML, it's about identifying an objective equation which gives minimized error. Or in case of a use case of AI, like say transportation, we talk about an optimal route tree with minimal cost. Or in case of a game, we're talking about a set of heuristics on a path which will lead us to finishing the game in each time. So if you see, there are several use cases around optimization which are at the core of what we call as the optimization requirement in any AI application. Then, what are the different optimization techniques which are typically used in context of games or transportation or scheduling, or even in the form of, say, let's say use case of scheduling. So let's say, for example, you want to create an optimal timetabling of a college with respect to maximum utilization of teachers and making sure that we use optimal number of teachers. So you see, there are several applications of the overall optimization as a phenomenon or a requirement in context of AI problems. But then, what has been the approach classically in optimization in a classical war sense, and how AI has kind of improved that basic notion is by use of a notion called constraints. Let's look at a key requirement for AI systems, namely approach for optimization. Optimization is a key necessity in AI-based systems because a typical AI program would involve search through several paths, and one of the possible paths can lead to a solution. So the idea is that you would like to look at optimization techniques whereupon you will try to reduce the overall path traversed length or weight of the overall path traversed, or look at the overall time taken to reach a goal, like say in a chess, whether the time taken by you should be minimal, or if you want to travel from one place to another, say for example in case of a scheduling problem, you would like to look at overall time taken to be reduced as much as possible. Or if you want to say, for example, look at a transportation problem, you want to look at overall transportation cost of the goods going from one place to another to get up by minimum fuel. Or in case of, say, for example, you have a solution for, say, a problem like timetabling of a school or a college, you'd like to have maximum utilization of the teachers with minimum number of teachers required, with minimal clash, etc. So if you see, all of them have constraints on cost, and there is an objective function which is related to either cost, in some form, either overall weight of the path traveled, or either in form of the total distance traveled, or in terms of the number of vacant slots to minimize, etc., etc. So in case of optimization, or even in case of games, it's typically about identifying optimal strategies so that you can reach the winning position faster and choose a path which is going to maximize your likelihood of reaching the winning point faster. So in all of this, we typically have a notion of optimization via some notion of a cost function. So cost function is basically a global objective function which is minimized in the presence of several input constraints. When you say several input constraints, typically they represent the truth on the ground as to what are the facts which cannot be violated. For example, in case of timetabling, we know constraints are that a person or a teacher cannot be in two classes same time. Same way, same class cannot have two teachers at the same time. So for example, that becomes a constraint on the overall problem formulation. So any input combination you try to achieve, while maximizing the overall throughput, which could be utilization, you cannot violate the constraint. So typically, any optimization function is written in form of maximize objective function. It could be in form of maximizing profit or minimizing cost or minimizing the time. Some are negative in terms of objective, some are positive. So for example, in case of utilization, it's maximization. In case of cost, it's minimization. In case of total distance, it's minimization. And in the presence of some constraints, it cannot be violated. Again, constraints can be of two types. It can be soft or hard. Hard means which is basically which can not be violated at any cost. Soft means which can be violated, but we try to minimize the number of violations. So if you see, any optimization function in AI can typically be written in form of an optimization function with a corresponding objective function and several constraints as a hard or soft. But then what are the techniques from AI which is coming in picture? Conventionally we talk about OR as the area, or operations research as the area which has methods which are related to solving these optimization problems, either by formulating something as a linear program or integer program or a combination of integer, linear and both in form of integer linear programs. But where AI has come into the play is by introducing a new paradigm called constraint programming, or which is proved to be orders of magnitude better in terms of optimization possible by comparing them with conventional OR techniques. So what exactly is meant by a constraint program? Constraint program is basically a set of techniques which use the notion of, what we call as backtracking and constraint satisfaction in combination. To look at constraint programming, let's take a simple example. Let's say we are talking about a program like say 4 queens, right? We take say 4 queens as a problem where we're supposed to place queens one after another so that none of the queens attack each other. What is the characteristic of a queen attacking a queen? It cannot be on the same diagonal, it cannot be on the same row, or it cannot be on the same column. So you start with your place can be placed in either first position, third position, fourth position as the first choice, right? First one you can place either here or here or here or here. But now, once you place the queen in the first position, for the second queen, you're automatically excluded from placing it here or placing it here because of the reason that they will attack each other. So we can say there is something known as a attack Q1, Q2 is true if they are either on the same diagonal or they are on the same row or they are on the same column. So given that this is not true for 1 and 2, the only position possible for the next query, Q2, will be 3 or 4. So what we have seen here is a local pruning happening because of a constraint like attack Q1, Q2, where we're talking about Q1, Q2 not being in any of the positions where they're either on the same diagonal or same row or same column. So what that has helped us is it has pruned the search space and effectively placed what is known as local constraints on the overall solution so that you don't have to unnecessarily traverse the whole path and prune it there itself and reduce the amount of search space required. Extending this notion of local pruning is a definition known as consistency. Means any global solution should be consistent locally also. Means it should also satisfy local constraints. So for example, if you take any global solution, let's say Q1, Q2, Q3, Q4, right? 4 queens are there present here. So you should make sure that it is making sure that it is locally satisfying all kinds of constraints. It could be unary constraint, saying that a queen can only take between 1 and 4. You cannot have some queen which is in 5th position, right? So the unary constraint says that all the queens should be between 1 and 4. That is primarily a constraint which is effectively placing something like a 1 consistency on the overall solution. So you cannot have something like Q3 equal to 5. You can only have either 1, 2, 3 or 4 for any values. Now coming to, let's say, any two Q1, Q2 or Q2, Q3, Q3, Q4. Any of the pairs of variables, there we have the constraint known as should not attack each other. Means when you say when you're not attacking each other, means it should not have a form where they're either on the same diagonal or the same row or the same column. So whenever you're looking at a local behavior, let's say Q1 equal to 1 and Q2 equal to 2, you see that they are the same diagonal. So they are violating this constraint of attack, and hence they will not contribute to the global solution. So therefore, you can do local pruning of the solution and thereby optimize the search space. Let's say take the same thing. Suppose you start with Q1 equal to 4. Then you know that Q2 cannot be 3 or Q2 cannot be 4 because they are the same diagonal on the same. So you can actually use only Q2 equal to 3, or you can use Q2 equal to probably 1. Sorry, 1 is also the diagonal. So probably only one which is remaining here is Q1 equal to 2. So now given this kind of a constraint, what we see is a local consistency criteria like unary consistency or binary consistency, which is also known as R consistency, is able to constrain the search path locally such that the global path is obtained optimally, because every global solution to a constraint should satisfy all the constraints in the system, whether it's unary, whether it's binary, which is R, or it will be ternary, which is also known as path consistency. And the whole stream of techniques from constraint programming are basically a set of techniques with consistently checked for unary, binary, path consistency, etc., and thereby offer better and local optimization techniques for removing irrelevant search paths and thereupon improving the path for optimization and thereby in the order of magnitude better solutions than conventional linear programming solutions.